Welcome to The Explainer. Today, we are diving deep into how different applications talk to each other securely using something called the Model Context Protocol, or MCP. It really all comes down to a secure digital handshake, and we're about to break down exactly how that works. So here's our game plan. We're going to start with the problem, this idea of a closed door. Then, we'll introduce the key, which is OAuth 2.1. From there, we'll walk through three very distinct types of digital handshakes and wrap it all up with the absolute essential security rules that keep this whole system from falling apart. All right, so picture this. A brand new client application tries to get information from a restricted MCSP server for the very first time. It has no idea what it's doing. It just shows up and, well, it gets stopped cold. And this is what that app sees, an HTTP 401 unauthorized error. This is really just the server's way of saying, whoa, hold on, I have no idea who you are, you gotta prove your identity first. You can think of it as a bouncer at a club, just blocking the entrance. So how does that client get the key to open the door? Well, the answer isn't some brand new, complicated thing. MCP builds on a really robust, industry-standard framework that, honestly, you probably use every single day without even thinking about it. That foundation is OAuth 2.1. Think of it as the universal rulebook for negotiating access between services. It's the magic that lets you sign into a new app with your Google account, or let a photo printing service access your photos, all without you ever having to give that service your actual password. Okay, so let's jump into our first and, by far, most common scenario. This is what happens when an application needs to do something on behalf of an actual person, a human user who has to give it the green light. So, for example, think about an app that needs to access your calendar to book a meeting for you. How does that possibly work without you just handing over your username and password? I mean, that would be a huge security nightmare, right? So the whole process kicks off with that rejection we saw just a minute ago. The client makes a request, and the server just says, nope, not without proper authorization. This is actually the critical first step that gets the whole security dance started. Now this is where the magic happens, because the user gets directly involved. See, the client never asks for your password. It can't. Instead, it sends you over to the official gatekeeper, the authorization server. That's where you log in securely, and then you see that screen that asks, hey, are you sure you want to let this app access your calendar? The moment you click yes, your job is done. The authorization server then gives the client a special one-time use code. The client takes that code, and in a totally separate, secure back-channel conversation, it swaps it for the real prize, an access token. And that's the beauty of it. The user approves the access, but never actually handles the final key. Now, this entire back and forth is protected by a super important mechanism called PKCE. That stands for Proof Key for Code Exchange. And it's not optional, it's mandatory for all clients using MCSP. Just think of it like a secret handshake within the handshake that proves the client who started the request is the exact same one that finishes it. Okay, that user flow is great, but what happens when there's no human around to click an approve button? How do automated systems authorize each other? Think about a script that runs every night to automatically check the inventory at a store. It needs access to that inventory system, for sure, but there's no user sitting there to log in for it. It has to act all on its own. And that is exactly where the Client Credentials Grant comes in. It's designed specifically for these machine-to-machine situations. There's no complicated dance with a user. Instead, the application just uses its own pre-registered ID and secret to ask the server directly for an access token. It's a much simpler two-step handshake that basically says, hey, here are my credentials, now give me a token. Okay, now let's kick it up a notch and look at a more advanced scenario. What if the server you're trying to talk to doesn't even want to handle logins itself? What if it wants to delegate that trust to another or more specialized service? So in this model, the MCP server completely outsources the job of verifying who the user is. Imagine a big company that uses a central identity provider, like Okta or maybe Google Identity, to manage all of its employee logins. The MCP server doesn't have to deal with passwords at all. It just has to trust that the identity provider is doing its job right. So as you can see, the MCP server ends up acting as this really clever middleman. The client kicks things off, but the MCP server immediately sends the user over to that trusted third party to log in. Once the third party says, yep, this person is legit, it sends a code back to the MCP server. And only then does the MCP server issue its own token back to the client. You know a secure handshake is only as strong as its weakest link. So a protocol like this really depends on everyone following the rules. Let's go over the absolute non-negotiable must-haves for any MCP setup. Now, these are not just suggestions, these are hard and fast requirements. For instance, all communication has to be encrypted with HTTPS to stop people from listening in. Servers must validate where they're sending a user back to after a login to stop attackers from hijacking the process. And of course, tokens always go in a secure header, never in the URL where they could get logged or leaked. And, like we said, PKC is absolutely not negotiable. But wait a minute, before any of these handshakes can even start, the client application has to solve a really basic problem. It needs to know where to even go. Where are the correct authorization and token doors located? So the best practice, the recommended way, is for servers to just publish their endpoints at a standard, well-known web address. The client can just go to that URL and get all the info it needs. Now, if a server doesn't support that for some reason, clients have a fallback plan. They have to try these default paths. It's discovery first, defaults second. And when you really look at the core security pillars of this entire process, you can see how much it relies on just a few key ideas. Securing the transport with HTTPS, that's the biggest piece of the puzzle. But right behind it is protecting the actual authorization flow with PKC. Those two things together really form the foundation of a truly secure system. Of course, things go wrong sometimes, and when they do, the server gives really clear feedback. A 401 error basically means, I don't know who you are, you need a key. A 403 forbidden is different. That's, okay, I know who you are, but you don't have permission for this. And a 400 bad request just means you're not even asking me in the right way. So we've seen how MCP creates this really standardized, really secure way for applications to connect with each other. But as this whole process gets more and more automated, it brings up a fascinating question. As we automate all of these digital handshakes, how do we build systems that aren't just mechanically secure, but are fundamentally trustworthy?